Hello, my name is Keh-Harng. I will be doing a presentation on what I've worked on for my final project, which is document domain resampling framework. Okay, so let's start from the beginning. A little bit of background information on resampling. So why do I want to resample? Well, to put it simply, it is to avoid reporting on inflated evaluation score due to model overfitting on the training set. So here's a little example which has nothing to do with NLP, but here it is. This is a decision tree model that is purposely made to overfit on a particular set of training data. And you can see that by evaluating this model on the training set itself, I've obtained an extremely good accuracy, which is 1. You can't really get better than that. But anybody who actually looks at the model will realize that this is probably not as good as it really is. I mean, if you look at the complexity of the entire model, it seems that it's simply putting everything into every single leaf of the tree. So how are we going to avoid getting an inflated evaluation score? The basic idea stems from a train test split of the training data. So normally you will train a model on the entire set, and if you're doing training set evaluation, you will then evaluate the model on also the entire training set. But what if we split the data into 2 parts? Then you will have a part of the data that is being used to train a model, and another part that is being used for validation purpose or testing purpose. Now, there are, however, some issues with this approach. The very first one is, what if I want to change the model, like tune the parameters, to improve its performance? Well, remember that the model is being evaluated on the validation set, which is not supposed to be used for training. So if you change the model parameters, and then you retest the model on the validation set and see that the score has increased, you keep doing this, you're essentially training on the validation set, and that is a big no-no. Right, because you're going back there, you're going to be reporting on the training set performance again. And also, we want to avoid any possible sampling bias caused by the split here. For example, let's say we have data for, say, a 100-meter dash, and 50% of them are from male athletes, and 50% of them are from female athletes. Then we want to split 30% of the entire data and just put it away as a validation set. Now, let's say for some reason, due to a stroke of luck or the opposite of luck, that 30% of this validation set, right, like 30% of the data that's said to be the validation set, are all male. In that particular case, first of all, your training set will have way more female than male. Your validation set are obviously all going to be male. So you're going to have some sort of bias here, just because of the way you split the data. So how do we fix this? The solution is to do essentially repeated random resamples, and then aggregate the evaluation scores on each with, once again, the test train split philosophy. So for example, our first iteration could be something like this, where we split the data roughly down the middle, and we train a model here, evaluate a model here. Then we do it again, this time flipping the roles, right? So this time we train a model here and evaluate here, and the final accuracy will be just the average of the two. And this is actually a twofold cross-validation, right? Because it involves exactly 2 validation folds and 2 training folds. And here I have recomputed the model accuracy, the model performance, using a 10-fold cross-validation on the very big tree I made before. And here you can see that a holdout set, the validation set accuracy for the entire tree is actually only 0.64, 0.65. But once I estimated the accuracy using the tree, so using cross-validation and came out to be around 0.64 as well, much closer to the true performance of the model. Okay, now that we have some ideas on what resampling is, we can all try to extend this to a text retrieval problem. And of course, by doing that, we're going to encounter some complications. The very first thing that pops up is the fact that the features in a text retrieval problem, which is the text corpus, they're usually separate from the responses, which are the query relevance judgments. And these two are linked together usually by something like a document ID and a query ID. So the response file, the relevance judgments, will just contain a list of like the query IDs and which documents have what kind of relevance to this particular query ID. Now, after you resample the document, because we're trying to do document domain resampling, you're going to have some of the IDs missing from your resampled corpus. And depending on what kind of toolkit you're using, the entire document, the entire corpus may have a completely new document ID index afterwards, because they might be automatically ordered based on what lines are there in the corpus. This means that your query relevance judgments need to be mapped after each resample. There's also the fact that a lot of times, like current NLP toolkits, they evaluate things based strictly on training set evaluation, so they don't exactly support the idea of train test split. In fact, what does this even mean in a text retrieval context? We're going to get into this later. Then there's always the problem of performance, which is the fact that you now have many sets of many documents. Those things are going to be naturally slow. There are going to be so many documents that sometimes you will need a lot of memory to just keep them there and process them. This is not really the focus of this project, so I mean the whole thing is kind of done as a proof of concept, so we don't really care about this. Alright, now the current implementation of the framework is basically organized into 3 different layers. The first layer, which is the most basic and the most general, is the resampling layer. And these basically provides tools for data partitioning and generation of all the support files, like the configuration files for the resampled corpus, document ID mapping that I've mentioned before, etc. And then there's the evaluation layer, and this is meant to provide support for the train test split methodology. The current implementation also allows modular ranker to be used for the evaluation, so you can test out different models if you have, or if you've written your own ranker and you want to use it. Right now, there's like a default BM25 ranker, and there's also support for logarithmic NDCG to be used to compute the retrieval score or to evaluate the retrieval performance. These are implemented by simply interfacing with Meta Toolkit, which you can find right here. Alright, and finally there is a testing layer, and these are kind of like template codes that show a little bit more like advanced use cases. And in fact, I use this to sort of generate the statistics required in order to study the efficacy of this resampling framework. Alright, so to get it started, we have to first look at how the data should be formatted. And they are assumed to be organized in a so-called line corpus format. So essentially, you have a giant text file with like each document represented as a single line in a text file. And then there are both judgments and query files, and they have to be provided in separate text files as usual. The judgments are stored as a mapping between query ID and document ID per line. And you need to put all these data into a root folder. So in the root folder itself, it just contains the configuration file, and other things like the collection of stop words that you're going to be using. And then you will have like a subfolder that contains the, let's say, the name of the subfolder name, that's like dataset, whatever dataset is, and that contains the actual corpus and other things like, you know, query relevance and the actual queries. To make this more clear, I'm going to show you an example of data that I have used to test the framework. Okay, so here is not actually the root folder. Here I'm just showing you the repository after you first download it, and here I have the sample data folder, the Cranfield set, and you can see under the root folder of the Cranfield set you have the configuration file. Here this is just saying that, you know, all the data including the configuration lives under the prefix /Cranfield. Stop words is right here, so you can see that it's listed right here. And then the data set is going to be inside a folder called Cranfield. So Cranfield, the corpus format is line.toml. You see that right here. Then you have a bunch of other things like what kind of filters you're going to be using to generate the inverse index, etc. That those of you who have touched meta before will know what this means. But the most important thing is that you have to get the files listed correctly. So I recommend to look over this and see how it is organized. And you can see that under the subfolder for the dataset, you have all of the other files like the query relevance, the queries, line.toml, and then there is the actual corpus itself. Okay, let's take a look at the organization of the resampling layer. The functions provided by this layer are essentially all stored in the file base.py and base-helpers.py. And this layer is meant to be used as a building block to construct various resampling methods to suit the user's needs. The most important functions are sample, and this is if you are given an index data array for a corpus with j documents. So essentially this index data will be going from, say, 0 to j-1 in a sequential order. It generates a sorted array consisting of n randomly sampled indices from index data. And there is also complement. So if you're given a full index array and a subset of the index array, this returns the complement of the subset from full. So essentially sub plus its complement will be equal to full. Then finally there's gen data folds, and this is if you're given the path to a configuration file for corpus data, and the dictionary that contains basically the indices of each fold, each of the documents contained in each fold. Then this actually carries out resampling, so you will generate all of the resampled data sets, data folds, the corresponding data structures, the configuration files, the mapping, etc. So with all three functions, user is able to basically make any resampling methods he wants. And let's take a look at how it is used in a very simple case. Alright, so here I'm trying to essentially create a twofold cross-validation, and from base I'll import any of the functions. Then first I'm going to make my dictionary object here. I'm going to try to do this for the Cranfield set, and I know from past experience that the Cranfield set contains 1400 documents. If you don't know this, you can always just read through the corpus yourself and try to determine how many documents there are prior to using this. And now I'm going to try to generate the first test fold. since there are exactly 2 folds, I know each test fold contains 700 documents. So I'm going to sample 700 documents, 700 indices from the full index, and I'm going to say replace to false so I don't redraw the same documents more than once. And after that, I can find the train fold, the first train fold, by taking a complement of the test fold, and I'm going to put the train fold into the dictionary. Then I'm going to do it again. So first I'm going to try to find the rest of the indices that haven't been into any of the test fold by doing a complement on the test fold that has already been drawn before. So I will call this rest. Then I'm going to try to draw 700 documents from rest. I'm going to call out my second test fold. I'm going to find the complement of the second test fold to get this the train fold of the second fold, and I'm going to set that to the dictionary. And finally, I'm going to use this to generate the data folds by giving it the path to the configuration. And maybe we can try to run it and see what happens. So inside test code Pi, I've actually done basically that, except I'm making use of a generic k-fold cross-validation that I've written and included in base to do basically the same thing, right? And here k is set to 2 because we're only interested in twofold. And now that's finished, let's take a look at what happened in the Cranfield dataset. So again, this is the Cranfield set. You go in there and go into resampled folder. You can see that it has generated 2 folds. Each fold contains a test fold and a train fold. If you go back here a little bit, you can see that it also has a configuration file for each fold, so you can load it very easily and generate their inverted indices. Okay, and now we're going to talk about the evaluation layer. The evaluation layer basically provides the tools you need to evaluate whatever ranking models you're using to retrieve the documents. This also supports the train test split methodology that I mentioned before. The single most important function is pretty self-explanatory. It's called evaluate, and it allows you to specify configuration file path for a test fold or the test set, the configuration file path for the training set. So essentially your ranker will be ranked, each of the variables that it uses will be extracted from the training set whenever that is applicable, and also the data, the document you're trying to rank. However, the documents that it's trying to rank are all going to come exclusively from the test set, because those are the documents you're trying to make a prediction on. It allows you to specify a ranker, so you can write your own ranker and plug it in if you want to, and also its corresponding model parameters in a dictionary file or a dictionary object. You can specify a result path to ask it to write the evaluation results into a text file over there specified by the path. This cutoff value is used as a parameter for the underlying NDCG scoring function. So basically your NDCG is used to actually evaluate the model performance on each of the query. And this cutoff tells that you're only interested in retrieving a maximum of 10 documents. Now back to the test code that we have used before. So up to this point, we're just generating the twofold cross-validation resample data, and here we're actually going to try to evaluate it. Right now, I'm only doing it for the first fold, but you can see that you can do it for the second fold too if you want to. And after that, you will just have to aggregate the results to take the average in order to get the cross-validation estimated evaluation. Okay, so now that we know the basic working and the building blocks of the document domain resampling framework, I did a little bit of extra testing to see if this is actually something worth doing. Um, and the result was a little bit surprising, to say the least. So here I'm going to outline essentially what I did to test it. This is not relevant to the function of the framework, by the way, so you don't have to read this if you're not interested. So essentially what I did is first I got my hands on a very large corpus called AP News. I split it into two disjoint sets, so set 1 and set 2. I put set 2 aside as a held out validation set. Okay, so set 2 essentially is just put aside completely and I'm never going to touch it again until much later. Now set 1 on the other hand is further split into 5 disjoint sets. I'm just going to call it like S11 all the way to S15. And these 5 sets are basically the training data that I have. So essentially I have 5 sets of training data, so I can do the test 5 times. Then the idea is to get evaluation scores on a BM25 ranker using 3 different ways to evaluate it. So the first way is just 5-fold cross-validation using the resampling framework. Second way is your usual training set evaluation. So basically retrieving documents and evaluating documents all on the same set, right? And finally there is the test set evaluation, which is to try to rank documents from the held out set S2 while only using like quantities computed from the 5 disjoint sets S11 to S15. And judging from what we've learned so far about resampling and overfitting, the expectation is that training set is going to overfit, so it's going to have the best evaluation scores compared to test set and FIFO CV. And chances are, if the model is overfitting quite a bit, then this will be much higher compared to the others as well. And FIFO CV will hopefully be quite close to the test set evaluation. The test set, since it has never been used and is during training, and it's quite big, we can sort of consider it as the true performance of the model. The reason why there are 2 kinds of BM25 being tested here, vanilla BM25 and research BM25, is because I want to see what happens if you try to purposely make the model a little bit more prone to overfit. And that is what the grid search is for. So the grid search BM25 simply does a grid search on its training set and uses a training set evaluation to try to see if we can make the BM25 evaluation score as high as possible. And when it does, after it does that, you will find the parameter that gives its maximum score. And then when we're doing all these evaluations, you will simply use those parameters to plug it in to the model itself before the evaluation. Okay. So here's the first surprising bit. This plot shows you the mean, the average NDCG with different evaluation strategies. You see the red dots here. They're produced by cross-validation, and they're quite low. The test set performance, test set evaluation scores, are represented by the green triangles here, and they are very close to the training set evaluation scores. And what's even more surprising is in the grid search case, the training set evaluation score is actually lower than the test set evaluation score. So this got me thinking that something doesn't quite make sense. I mean, how can a model possibly underperform on its training set compared to its inner wild performance. Okay, so to investigate this further, what I did here is I plotted the difference between the NDCG scores uh, between the test set and the training set. So this is the S2 minus S1 whatever, basically, um, and this is done per query on the regular BM25. Now you can see that since this is a difference and it's a test minus train, so basically every time you have a positive value, the the model training set performance is basically underestimating the performance. Now they are also color coded from black to red using a quantity that I call proportionality 10. So what this quantity is it's basically the number of relevant data for this particular query divided by the number 10 to a maximum of 1. If you think about this, what happens is that since we're doing a retrieval cutoff at 10 documents, if you have 10 documents already inside whatever it is that whatever test set you are evaluating on, then you can potentially get the maximum NDCG, right? If you don't have it, that's normally fine because the NDCG is normalized with regards to the maximum value that you can possibly get. However, you will also make the NDCG value a little bit less finer grained. So essentially, by losing one document, you could be losing a lot of NDCG. So it's more likely for you to deviate from the test set performance. The test set itself is very large by design, right? So normally you will have more relevant documents compared to everybody else, so its NDCG value will be more finer grained as well. The biggest problem though happens when your proportionality 10 constant is at 0, because that means that your query essentially contains no relevant documents. Like your query doesn't have any relevant documents to work with. So the maximum NDCG you can possibly get is 0. And as a result, the NDCG you can possibly get is 0 as well. Now, if the test set, the true set S2, actually contains relevant documents for that query, then you're already losing on the starting point, right? Like you will always underestimate your model performance, no matter what. So essentially, what you should take away from this whole thing is that red dots are good, black dots are bad. And you can see that the training set fortunately still contains quite a few red dots. Let's see what happens with the cross-validation folds. Okay. As you can see, there are nowhere near as many red dots compared to the training set. And this is, in a sense, sort of understandable, because if you look at this, what is the most likely factor in determining how many relevant documents you have? The total size of your corpus, right? And for the training set, if we look at how things are split, here, set 2, the true set, contains half of the original corpus. And the original corpus actually has around 160,000 documents. So set 2 has about 80,000 documents. Now set 1 also has 80,000 documents, but it's further split into 5 sets, which are the training sets, right? So each of them will have around 16,000 documents. Then we're going to carry out 5-fold cross-validation, which means that each of the 5 training sets will be further split into 5 folds. So each fold only contains about 3,200 documents. Therefore, the chance of having a very low proportionality 10 constant for a fold is very high. And that is probably the reason why the cross-validation evaluation score is so severely bottlenecked at such a low value. Alright, so here's a short summary of the things what we have talked about. So the current state of the resampling framework is that it does provide flexible building blocks for users to build different document domain resampling methods, and you can also use it to build more involved methods such as nested cross validations, and nothing will really stop you from doing that. However, the resampled evaluation scores, they do contain large pessimistic bias, and this is due to the lack of considerations for relevant documents being eroded during the resampling process. And to combat this, the simplest way I can think of is probably data stratification. So you want to make sure that you at least have some relevant documents. And let's say if you don't, like it is simply impossible, then you should probably come up with some ways to dynamically weight your query relevance evaluation scores, so you can take away the weight from queries that simply have no relevant documents whatsoever due to erosions, and give the weight to queries that are actually capable of getting relevant documents. So this is it for my project presentation. I know it's very long. Thank you for your time.